Up to the point in time of Ernest Rutherford and just before Niels Bohr, the basic understanding of the atom was that it had a positively charged nucleus surrounded by the electrons. The work of Niels Bohr opened a new frontier of the understanding of how electrons are around the nucleus of the atom. To understand the work of Niels Bohr, it is first necessary to study the visible spectrum, since it plays an integral part of the understanding of the quantum theory that Niels Bohr used to explain his finding. So this here is a drawing of the visible spectrum. And we know how the visible spectrum is produced. It is produced when white light is resolved into its various colors. It can happen when you pass light through a glass prism. The visible spectrum, of course, is only a small part of this entire larger magnetic spectrum here. So this tiny part here is what constitutes the visible spectrum. Now, one or two little things about the visible spectrum that's important for us. I'm going to read that and then explain. The German physicist Max Planck believed that light is composed of photons or packages of energy, and that each photon has its own fixed amount of energy called a quantum. The visible spectrum is composed of a series of different photons jam-packed together. The amount of energy of a photon is given by this equation here, okay, where h is Planck's constant and v is the frequency of the photon. Go back a little bit to the spectrum now and talk a little bit more about it. See, each photon here has a specific wavelength and frequency of vibration. So what we'll do here is this. We will remove a few of these photons and then make comparisons with them, right? Doesn't matter, okay? So what he's saying here is this. Each one of these photons here travels with the same speed, which is found by multiplying its frequency by its wavelength. The wavelength of the photons increase in that direction there. So it's getting bigger in this direction. But since they travel at the same speed, the frequency with which they will vibrate must increase in this direction. So the frequency here times the wavelength must be equal to the frequency times the wavelength here. But something else is involved here. As the frequencies of the photons increase, so do their energies. So based on this equation here, where energy is given as E times Planck's constant times V, where this is constant, we can see that the energy is directly related to the frequency. So any photon that has high frequency will be high energy. Let's compare the energy of these photons. If we compare the energy of this guy with this one here, definitely because this one has a higher frequency than that one there, this photon here will have more energy than that one there. In the end, we can say that this photon here will have the most energy compared with the others there. So as you move from left to right of the spectrum, the energies of the photons increase in that direction. So now we'll move on to what is called the emission spectrum of hydrogen and give Bohr's explanation of how it was produced based on his model of the atom. I'm going to show you this and come back and read for you. This here is what is called a gas discharge tube, or specifically we call that a hydrogen discharge tube. Basically what it is a cathode ray tube that is filled with hydrogen gas, or it can be filled with any gas that you want to investigate. So in this case, we're filling it with hydrogen gas, and of course it has its two electrodes. It has a cathode and it has an anode, and it is connected to a power source. This here is a power source that has an adjustable voltage. You can vary the voltage by manipulating that knob there. Above that is placed a diffracting grating. A diffracting grating is a stiff piece of plastic with a series of alternating opaque and transparent apertures with width comparable to that of the wavelength of light. So you see the spaces here? The gray areas are opaque and the clear ones are transparent. All right? But the transparent parts, the width of those, are small enough to be comparable to the wavelength of light. So we're trying to see what happens when the hydrogen discharge tube is subjected to a variable voltage source. That is, we start with the voltage at 0 and gradually increase it. Okay, and then someone will be watching through this diffracting grating here to see what will happen as the voltage across the electrodes is gradually increased. So I'm going to go back there and read for you what this figure here is trying to depict. The figure below shows what happens when gaseous hydrogen is placed in a glass discharge tube whose electrodes are connected to a Bohr source of adjustable voltage. Starting with the voltage at 0, it was gradually raised and observations were made of the discharge tube through a diffracting grating. At some point, a line of red color was first observed, which was subsequently followed by 3 other lines of different colors as indicated below. The collection of these lines is called the emission spectrum of the element hydrogen. When samples of other elements in their gaseous states are placed separately inside the discharge tube, the different lines will be observed for them. So let's go back and see what happens here. Starting with the voltage at 0 and gradually increasing it, person watching here saw 4 different colors. So at a certain voltage, a red photon appeared. As the voltage was increased, another photon appeared. Further increase of the voltage produce another photon, and then lastly, I get that regardless of how high the voltage was. How do we now give an explanation of that? So Bohr will give an explanation of that based on his interpretation of the model of the atom. So I'm going to read here for you now. To explain the emission spectrum of hydrogen, Niels Bohr proposed that electrons are found outside the nucleus of an atom in discrete regions with fixed energies. He called these regions of space energy levels or shells. Electrons cannot be located anywhere else except in these regions. The farther away electrons are from the nucleus, the more energy they'll have. So I'm going to show you the model proposed by Niels Bohr. So what Niels Bohr is saying is this, that this is the nucleus here. He's saying that electrons can only be found in these areas here, like here, it can be found here, okay, here, this arrow, it can be found here, it can be found here, it can be found here. They can't be found in these transition areas here between these shells. They can be found here, they can be found here, they can be found here, they can be found here. So Bohr is saying this, that each shell here has a distinct amount of energy. Okay? So if an electron is found here, we'll have a certain amount of energy. If the electron is found here, we'll have a different amount of energy, but it'll be more than what you're having with the shells lower down. So this shell here will have some energy, that one more, that one more, that one more, and stuff like that. So this is the model proposed by Bohr. How did he use this model here to explain the emission spectrum of hydrogen? So this is the deal here. When the voltage is increased across these electrodes, of course we know that electrons or cathode rays will be coming off the cathode here and moving towards the anode. So obviously as we increase the voltage here, the energy with which these electrons are peeled off will increase. They collide with the hydrogen atoms, and they also collide with the electrons that are found in these atoms. So let's go back and try to explain what is happening there, how Bohr gave his explanation. Why don't we read here and then go? Bohr theorized that as the voltage of the discharge tube was increased, the energy with which the electrons from the cathode were ejected increased proportionately. According to him, these electrons collided with hydrogen atoms in the tube and bumped the orbiting electrons from lower energy levels to higher energy levels. When this happens, the electrons were said to have undergone transitions and the atoms became excited. The atoms in these unstable excited state quickly reverted to the more stable ground states by allowing the electrons to fall back to the original energy level. As a result of these transitions, electrons falling back from a higher energy level back to a lower energy level, quanta, plural for quantum, of energies were released. So this is what is happening. Let's go back and try to explain again. So what Bohr is saying is this. He's saying that the electrons here are orbiting the nucleus just like the way the planets are orbiting the sun. He called these electrons the orbiting electrons. So what he's saying is these electrons from the cathode are coming towards the anode. Invariably, they will collide with the hydrogen atom and will bombard these orbiting electrons. If a collision happens between a orbiting electron and a bombarding electron, Bohr is saying that this electron here, because it's in a fixed energy state, can jump to a higher energy level, like this one here, okay? But in this state, the atom is said to be excited, and it doesn't want to remain like that. So the electron reverts back to its original position here. In so doing, it gives off a photon of energy that corresponds to the difference in energy between this shell and this shell. Okay? So you get an energy. So what Bohr is saying is this. If this electron gets more energized as a result of an increase in the voltage, then it will be capable of not only knocking this electron up there, but it's capable of promoting to a higher energy level here. Okay? The difference in energy here is greater than the difference in energy here. So when this electron falls back, it will produce a photon of energy that was greater than this one when it fell down back. And more can happen like that. With greater voltage, this get more energy. It bumps the electron to an even farther orbital there, or a shell energy level. So it reverts back to its original position now. It will give off a photon of energy that is even higher. And that is what he used to explain the emission spectrum of the hydrogen atom. See? So this one is produced at low voltage. This one at a high voltage, slightly higher voltage, and stuff like that. So these observations here enabled Bohr to say, you know what? Electrons are not arranged in any haphazard manner around the nucleus, but they are found in discrete energy levels or shells around the nucleus, and that the electrons are orbiting the nucleus like the planets are orbiting the sun. Also, as you move away from the nucleus, the electron gets more and more energy. One thing more to notice this is that there is this paragraph. In 1922, Bohr was awarded a Nobel Prize for his work, but his theory is only limited to the hydrogen atom, since it could not explain the emission spectra for other elements other than for hydrogen that had one electron. Flame test for some ions. If the salts of certain compounds are burnt in a Bunsen flame, they produce different colors here, and we call that this flame test. Each particular element will have its own flame test. If you put different gaseous element into the discharge tube and you look at it through a diffracting grating, you see different spectral lines. The same thing will be observed if these flames are viewed through a diffracting grating. Each one of them will give their own spectral lines. And these here are the spectral lines for these here. Let's suppose you have gaseous calcium inside the discharge tube, and you viewed it through a diffracting grating. You will see these lines, and these are the other ones here also that you see there for these ones here. Of course, that's how fireworks are made. Fireworks are created by putting salts of all of these different compounds together, and they shoot it up in the air there, and they have something to produce lots of energy to excite the electrons, to bump them up to a higher energy level. So when they fall back there, they will give off their own types of colors. Has been a very intriguing lesson. I hope that was helpful. You can always go back and look at the video. I just want to highlight a few points with respect to this figure here. A few scientists have discovered that there exist certain patterns in which radiations are emitted when hydrogen is used in the discharge tube. Recall that we said that the first shell is called a K shell, and it is given a principal quantum number 1, something you study more in grade 12. The second shell is called the L shell with a principal quantum number n equals 2. The third shell, the M shell, with principal quantum number 3. N shell with principal quantum number 4. A scientist by the name of Jacob Bohr noticed this. He noticed that only when a transition happens from n equals 2, means from the L shell upwards. In other words, if an electron is bumped from this level here to that level here, and it returns back, only then that a photon is produced that the eyes can see. Also, if it moves from this same one to another one here and it falls back, then that photon will be seen because the photons that are produced there are found in the visible part of the spectrum. So only these can be seen. If an electron is bumped from the first to the second, that will not be seen by the human eye because the receptors in the human eye cannot detect such type of radiations. As a result of that, a series is named after him, Jacob Bohr. So he called it the Bohr series. That is, when electrons are bumped from the second shell upwards, and when they do fall back, you get these spectral lines here that belong to the visible spectrum. Theodore Lyman now discovered another pattern. He found that if an electron is bumped from the first shell to the second shell and it returns, the human eye cannot detect that radiation because the photon that is given off here, or the quantum of energy, does not correspond to any in the visible spectrum. But these can only be detected in the UV part of the electromagnetic spectrum. So from 1 to 2, from 1 to 3, and backwards, 1 to 4 and backwards, these are only detected in the UV part of the electromagnetic spectrum. And then you have Friedrich Paschen, should be an S there. He discovered that if transitions are happening from the third shell upwards and backwards, then the energy that is given off there, or the photon that is given off there, is only detected in the IR, in the infrared portion of the electromagnetic spectrum. I just said, let me highlight that to you, so you'll come across that one day. So, thank you for that. And these are laid out here. Okay? You can take your time and read that later on. So that is a discharge tube that is filled with hydrogen gas. And the two electrodes of the tube are subjected to a very high voltage. In this lab here, we do not have an adjustable voltage, but except that we have a very high voltage. So we will not be able to change the voltage to a progressively higher and higher voltage, such that we can see the gradual production of those 4 lines we're talking about. So we'll have multiple kind of transition taking place here. What you see with your naked eyes right now is one color. And that is a blend of the four different colors or lines that are produced when hydrogen gas is subjected to very high voltage. Now, to see those four lines, we need to use an instrument that's called a diffracting grating that will enable that particular color that you see there to be resolved into the four different lines for hydrogen. So we now put this diffracting grating in front there. Let's see what we're going to see. So let's see. So you can see right now, yeah, we're getting some stuff there. See? So these are the lines that are produced when the hydrogen gas is subjected to very high voltage. You have multiple transitions taking place there. Okay, so these lines that you see in there, they represent the emission spectrum for hydrogen gas. And different elements, if you put different gaseous elements inside there, each of them will have the unique emission spectrum. Okay? This here is an example of a diffracting grating that we have spoken about before. What we want to observe today is what happens when white light passes through a diffracting grating. What we'll be using is the white light that is emanating from each of these bulbs in the chandelier here, and let it pass through the diffracting grating and then observe what happens. So here is our diffracting grating now. So when you're observing something that is very familiar to you, is very similar to the rainbow phenomenon. As white light passes through the diffracting grating from each of those bulbs, it is diffracted into its component photons that form what is known as a continuous visible spectrum. So you can see that each bulb there is producing its own phenomenon, its own continuous visible spectrum as its light get diffracted by this diffracting grating here. A similar thing happens in the atmosphere after a brief shower or some drizzle. The water vapor that enters the atmosphere causes light to be diffracted into its continuous spectrum, and it is seen as the rainbow. So this is what happens when light passes through a diffracting grating, white light. It forms its continuous spectrum. If any source that has a set of photons, but not the complete spectrum, it will be diffracted into those component photons as we have seen in the case of hydrogen gas. So this is the phenomenon of diffraction, and it happens when a diffracting grating is placed between any source of light that has different photons.